Hey kiddos, sorry on a 24-hour isolation hold from you while my antibiotics kick in. Anyway, I'm going to go over C4 with you so that we don't lose time. Reminder, test is on Thursday. I'll be able to go on over any of these ideas that don't quite make sense in class tomorrow. So, conservation of biodiversity. Remember that biodiversity means bio means life, diversity is the amount of organisms that are living within that area, okay? You have 6 understandings, 2 applications, and 1 skill. And the 1 skill is to be able to use or analyze the Simpson's reciprocal index of diversity, which clearly looks at the diversity of a region, right? So, first of all, you are going to look at some things that look at, or I should say you look at species that look at indications of how the environmental conditions are impacted by usually human impact. So indicator species are organisms that are sensitive to specific environmental changes. So specific pH changes, soil changes, light changes, something like that. And if they are present, scientists can conclude some things about that location, and if they're not present, scientists can assume some things as well, right? So like mayfly larva really likes dissolved oxygen. If you see mayflies, you probably have a high level of dissolved oxygen. These rat tail maggots don't need as much dissolved oxygen. So if I saw this when I walked to a stream, I would know one thing. If I saw this when I walked to a stream, I would know another thing, right? Get that? All right, so there's 2 calculations that you need to talk about. The first one is the biotic index, and then we're going to talk about the Sampson one. So how you do this, if any of you are in bio club, you did this, but you put the net in the stream and you kick sediment and dust or the soil from the bottom into the net, and then you pull up the net and you see what type of animals you have. So you can see this guy very simply doing this. Clearly you would want to do this with the stream flow, not against the stream flow, right? You wouldn't catch anything. So what you're looking at in the biotic index is just the amount of indicator species, okay? You're going to use this equation here. So number of individual species times the rating, and that you just get, or is provided, and then divided by the total number. So again, you don't need to remember the formula, you just need to know how to analyze the data. So here's my city. I have picked a site above the city, upstream, and I've picked a site below the city, downstream. So I'm going to look at the biotic index of the upstream comparatively to the downstream. Here's my equation. So here are the numbers of various species that I found within the upstream. Here are the numbers of the various species that I found in the downstream. You can see that I have E and F in both locations and D, but I don't have any others overlapping. Again, we're not specifically concerned about which species they are, just their amounts and their tolerance ratings, which are given to you. So 10 is, if I go back, clean water only. 1 is tolerates very polluted water. So species A is very, very clean, or will only hang out in clean environments, where something like species I will hang out in the dirtiest of dirty. So you can kind of just glance by looking at the types of species that are here and the tolerance ratings that it's possible that downstream is dirtier, right? And therefore would possibly have a lower biotic index. But let's actually go through the math. So I just recopied the equation down, right? All I did here in this little table was do the top part. So I took the number of species, so 12, times the tolerance rating, 10, and I put 120. Hopefully that makes sense. Now you see that it says the sum of, so that means I need to add all of these numbers together. So the sum of all of these together is 652. I then divide by the total number of individuals counted, or collected. And I only do that at each site. I don't add site A plus site B together. So the sum is 652 for site A, and I divide by 83. Got it? The sum for site B is 364, and I divide by 96. So if I do that math, I get 7.9 and then 3.8. Again, tolerance rating, clean level only, very polluted water. So you can see that, and it would make sense based on locations, that this water above the town would be cleaner and would tolerate a more abundant, unpolluted environment than down below, right? So that's just looking at actual biotic index values. That calculation does that. The next calculation looks at two really big things. It looks at what we call biodiversity, right? And when we talk about biodiversity, we talk about two components: richness and evenness. So richness is the amount of species present. So therefore, if you look at the sample, I have 6 butterflies, a dragonfly, and a ladybug, right? So I have 3 different species. That's richness. Evenness is how even is that population or species. So if you look here, I have 4 butterflies, or moths possibly, and I have 4 ants. So this species, or this, sample is really even because I have an equal amount of butterflies to ants. This species, or this sample, is not as rich as this sample is. But this sample is not as even as this sample is because this sample has way more butterflies. Hopefully that makes sense. Now when we calculate biodiversity, we look at both. So this sample A isn't better than sample B as far as richness wins over evenness. They're both present. So when we do this specific calculation, it's called Simpson's reciprocal index, and it looks at both richness and evenness. And the higher we call it a D value, so the higher that Simpson's reciprocal index, or D, is, the greater biodiversity you have. The lowest possible is 1. And that would just mean I found 1 type of species. It doesn't matter how much, but I found 1. And then the max value is equal to however many species you found. So let's say you found 5 species. But the catch is they all have to be found abundantly as well. So that's really rare in itself. So lowest is 1, highest is however many species you found in that sample. But again, that's pretty rare. So let me move my screen back over again. Here we have sample A, here we have sample B. We're going to use this kind of convoluted statement here, but it's really not that hard. So the first thing I need to do is get rid of this. Goodness. Okay, I need to count the amount of species that I have. It doesn't matter, I don't need to label which species. I can use letters, I can use numbers. I suggest that you use letters so that you don't get them confused with the counts that you're actually doing. So in this case, there are 6 butterflies, so that's species A, there's 6, there's 1 dragonfly, and there's 1 ladybug. Here, over here, there's 4 moths, or butterflies, whatever they are, species A, 4, and 4 ants. Hopefully that makes sense, right? We're not going to worry about specific names. Okay, then at that point, we start to do a sample calculation. So here's our thing over here. And we're just going to do sample A first. So N is the number of total organisms of all the species. So 8, right? 6 plus 1 plus 1 is 8. And then you take, just like you did in the degrees of freedom, whatever that number is, minus 1. So you're going to take 8, and then in parentheses, 8 minus 1, so 7. So 8 times 7, 56. We're good there. Then you're going to take the sum of all the individual species. So kind of like you did in the chi-square, kind of. So there was 6 times, in parentheses, 6 minus 1, or 5, so 6 times 5 is 30, plus 1 times 1 minus 1, in parentheses, or 0, so 1 times 0 is 0, and then that again for species C. So therefore you get 30 plus 0 plus 0, or essentially 56 divided by 30. And again, here our Simpson's reciprocal index is 1.87. Remember, 1 is the lowest. So that's actually not really good, right? All right. Now let's do sample B. Again, 8 total. So we'd take 8 times 7, in this case 56 yet again. And now we have 4, and then 4 times 3, and then plus 4 times 3. So 24 on the bottom, 56 on the top, 56 divided by 24, 2. Again, still not great, but it's better than sample A. So we would say that sample B has a slightly higher biodiversity. And that's what we're looking at in the Simpson's reciprocal index. It's all about diversity because it's the Simpson's reciprocal index of diversity, right? Okay. So there's just a few more fun factoids that I need to walk you through. And then we'll be done. Those are the two mathy things that you need to know. So we talk about extinction all the time. Extinction's always been a part of evolution. We will talk about evolution our next unit, and essentially those that are best adapted survived and those that aren't die. We know that that's caused by competition, by lack of nutrients, by resource partitioning, by a whole bunch of different things. However, our impacts, human impacts on the ecosystem, have greatly accelerated the rate of extinction, right? So we watched that video yesterday on the Arctic and how sea ice is going out, he's finding polar bears that are dying, all of those things. So we call any human environmental factors, we talked about this before, anthropogenic factors, right? It's just what we're doing. So if you see this word anthropogenic, that always means human influenced. So burning of fossil fuels, that's something that we do, clearly. Habitat destruction, pollution, overfishing, that kind of stuff. All of those things are important. Sorry, I had to get kids testing. Anyway, so we were talking about human activity and how it speeds up the extinction processes. However, we can also talk about the fact that we are realizing that, right? And we're making nature reserves. So nature reserves are huge, very beneficial for a few things. One, all the invasive species are not there, so they're controlled as far as not being brought in. Usually we can't exploit a nature reserve. You can't go logging in the middle of a nature reserve, right? You've protected endangered or extinct species, whatever that may be. Researchers are usually allowed in to figure out whatever research they want to do. And then, you know, it's just kind of a nicely thing. Most reserves are not privately owned, but they can be. And if they are privately owned, they're still protected by national law, which is kind of cool. There's a whole bunch of examples of nature reserves throughout the area. A lot of people think just terrestrial, so just land, but you can also have aquatic reserves as well, just an FYI. Okay, oops. So, what makes a reserve best? Frankly, there's a few just general principles. First of all, size. Bigger, the better, right? And if it is big, ideally it's big and all together in one giant clump. It's not in a bunch of little clumps. And if it has to be in little clumps, it's better to have the clumps closer than further apart. And if you have to have clumps at all, it's really a good thing to have corridors or little highways, like we do skyways or skywalks between those corridors. Okay? So, a few things. One, this image is in your ivory packet, but you can see that as island size increases, the number of species increases. So, we can infer, based on that, that the larger the size of the nature reserve, the more diversity you would have, right? Now, we have this thing called edge effect that's going to come into play here in a second. Why is bigger better? Well, I mean, we always say that, but really why? More resources, more breeding sites, the possibility of migration, more biodiversity. All of those things increase biodiversity, which is the huge keystone or what we hang our hat on when we build a nature resort.